Okay, so last time we left off at the beginning of section 2.1 about linear transformations. And I've given you the definition and a quick example. So now we're going to continue here. And I want you to first discuss when we have the property that the sum of two vectors afterwards, then the transformation applied is equal to T of EV plus T of U. Actually, this is a typo. So this should be, of course, U. Can you deduce that this is also true? Is this true? This is just to give you some practice with this notation. Any ideas how we could try this? Remember that the expression of the sum of alpha 1 v1 from 1 to alpha I vi from 1 to k just means that I want to abbreviate the sum alpha 1 v1 plus alpha 2 v2 all the way up to alpha abk. So I see someone Jancy wrote in the chat, expand and use linearity. Can you explain that?
Sure. So I was thinking of expanding the sigma notation to the one term plus the other ones.
Yes.
Then we
yes.
should
Exactly.
like T of A1 V1 plus T A2 V2.
Yes, exactly.
The coefficients.
So what the idea is basically what Jancy just explained, that we iteratively we just repeat the property 1 that we have for the transformation. So we view this large sum that we have here as just a sum of the first summoned and all the others together. So we basically we package them into this, and then we have reduced the problem to just having 2 summons, which is great because then we have the axiom 1. So this means we have now I starts at 2 and goes still to k, and we have alpha I vi still. Then by the axiom 1, we know that this is T of alpha 1 v1 plus T of the rest. This is 2 to k alpha I vi. Okay, how many times do we need to repeat this? I mean, we just see that this is now a sum with k minus 1 summons here, and when we do this more times, to be precise, k minus 1 times, we actually have this all written out. So we just more and more times. So we just apply this k minus 1 times. And then we have alpha 1 v1 plus the next one is the alpha 2 v2 that comes out. And then this continues to tf alpha k vk. Okay, is this now equal to the right-hand side? Or are we not done yet?
We have to use axiom 2 for each of them.
Yes, exactly. So we use axiom 2. And then this means that for each term separately, we use this, meaning that we can write alpha 1 outside. And we have T of V1, and we have alpha 2 times T of V2, and so on. And now finally, we have the right-hand side of this equation. Let me just write this again in a shorthand notation. This would mean that I have terms like alpha I times T of Vi, where the sum goes from 1 to k. Any questions? Okay, I hope this was this was a good warm-up for you. Because now we're going to have a proper discussion. So now I'm actually going to give you time to discuss, to think about this yourself. And what I want you to do is, well, I've given you one example and the definition. So I think the next step would be to decide whether these suggested functions, 5 are listed here, whether they are actually linear transformations or not. So don't do all of them. That's really going to take too long, but just pick your favorite one and then decide whether it is a linear transformation or not. So the question is it linear or not? It's going to be a function from one to the other, but is it linear? I'll give you 3 minutes, and then we'll resume. And if you have questions, just write in the chat, and I'll reply there, so that everyone has some quiet minutes to think. All right. Someone please choose a number and explain what you came up with. Sam.
Yeah, so I picked number 1, and I think it is not linear because if you take t of 1, 1, it is not equal to t of 1, 0 plus 0, 1.
The answer is correct. It is not linear. Let's just see how it violates the. So the claim is this is not linear. So you said you want to take t of 1, right?
Yeah.
And this would be 1.
Yeah. And then if you take t of 1, 0 and t of 0, 1, and that is not equal to t of 1, 1, because like it's not like.
Oh, sorry. So okay, let me. So you're saying that that 1, 1 can be written as 1, 0 plus 0, 1.
Yeah.
Yeah. And now comes the but. There's a problem because t of 1, 1. So this kind of calculation is best done like in 2 directions. So we want to say this has to be equal. What this means is that whenever I make an exclamation mark above an equation, then I mean this is supposed to be true, but it might not be true in the end. So this is supposed to be equal to t of 1, 0 because we can decompose. No, this is. I'm making it more complicated than it be. Okay, and now we use that. This is now axiom 1. If t was linear. So if it was linear, we would be able to use the fact that we can separate the t into t of 1, 0 plus t of 0, 1. Okay, and now what did you observe? What's the problem? What's the outcome?
Well, yeah, because both that equals 2 because like you're taking the max. And, like,
yeah, exactly. And the max here is still 1. And because 2 is not equal to 1, we have a problem. So this means this is not true. So this is contradiction. So this means it violates axiom 1, and therefore it can't be a transformation. And also notice how Sam didn't do like general proof, but Sam picked one particular counterexample, and that's exactly the way that it's easiest to verify such a counterexample. So that was very good. Adrian, you have your hand up.
Yeah, so I picked the second one, and I think the derivative is going to be linear, actually.
Yes, correct.
And to see this, we can just pick any 2 polynomials, P1 and P2, and then just look at the derivative of the sum of the 2 of them multiplied by a constant, or one of them multiplied by a constant. And then just by like the loss of derivatives, we can just take out the constant and it'll be the same.
Yes, exactly. So what Adrian said was we pick any 2 polynomials p of x, q of x in Pn of R, and then so we're going to use the laws of the derivative. And this is something that you learned probably someone in school, that when we actually apply d of dx, and now don't be don't be confused by the notation, because this quiz is all about abstraction. So now anything can simply be a linear transformation. And now in this case, as I suggested here, the name that we give this, I mean, we could just call this t, but it doesn't really matter. The name is d by dx. So d by dx takes an input, which is a polynomial, and gives back a polynomial. This is what this notation suggests. It's going from polynomials to polynomials. And what it does what it does is it takes a polynomial or a function, I mean, this should be a polynomial, and it just takes the derivative. So this means if we want to compute this applied to the sum of two polynomials, so we have px plus q of x, then this is exactly where the laws of the derivative come in, because this means you've learned that the derivative of a sum is just the sum of derivatives, d of dx, p of x plus d of dx, q of x. And you've also learned that if you have, let me pick C, a real number, then if you multiply, if you have a constant times a polynomial, then the constant is constant because it doesn't change with respect to x. So this means that when we take the derivative, this is another rule that you've learned. This will be C times d by dx of p. Well, your middle school or high school teacher didn't tell you that the derivative is linear, but this is essentially what they were saying. So we're just reviewing things that you already know with another language. So there's no reason that this should be. I mean, sorry, I don't want to say that this shouldn't be confusing, because maybe the first time you see it, it might be confusing, and that's okay. But the core of what we're doing is nothing new. We're just giving it one of the names, and we're observing that this law that you've learned many years ago is actually part of a more general structure of a linear transformation. So there's no difference between the laws of a derivative and, say, the laws of transposition of a matrix. Okay, I think we have time for one or two more. Oh, any questions? I didn't check. Any questions about this? Yuan, you have your hand up.
Yeah, I was wondering if you could define transposition for a matrix that's not 2 by 2.
Oh, absolutely. So transposition just means, what's the best way of phrasing this? You just mirror this along the diagonal. So let me maybe just not make this too rigorous, but if you have a matrix A11, A12, A1M, AN1, AN2, ANM, and you take the transpose of this, then all I mean is, actually in this case, I want this to be square. So what I should say is, let me make this into AN1, and then this is ANN. So if I transpose this, it just means I interchange the entries from the ij position to the j position.
Oh, okay. Okay.
So this means when I so this the entry n1 is going to be a 1n, because they have switched indices ij. So I could also say that actually this is not the best way to define it. This is probably confusing, but let me just finish this and then I'll give another explanation. So now here you have a n1 and here have a1n, and the 1, 2 that used to be up here is now down here. So this is how you can view it. You just fix the diagonal element, you just flip, you just rotate this along the diagonal, you just flip this. A more abstract definition is that aij, if this is a matrix with entries aij, and if you transpose this is going to be AJI. So again, the I and J flip.
Okay.
Okay, someone made a comment about Idris. You made a comment in the chat. You don't think that what is linear? The transposition? Can you explain? Oh, okay, that's fine. I guess it's always good. So notice that in this case, the operation of the vector space is not multiplication of matrices, but addition. So rotate. I'm not sure what you mean by rotation. I'm just flipping the entries. There's no coordinates or a vector space being rotated. So this is actually, in fact, linear. And the way we can prove this is if you pick. Actually, let me use the second notation because it's very similar. So if you just pick A and B, again, two arbitrary matrices. And the size should be n cross n. What I mean by this is, I mean, A11 is the first entry, A12, and then so on. And then we see that that the sum of A plus B, if we apply the transposition, then what is the sum? And the sum of two matrices is defined component-wise. So we just, for each index pair ij, we add the numbers that are in the matrix. So this means we're going to have aij plus bij. Let me transpose this. But now you can think of this as just the new entry in ij for the sum. So this means that we could even make this more suggestive. Let me take one more step in between. Say this is a plus b, aij. Maybe this is confusing. So what I'm saying is that if you write this out, maybe doing an explicit example 2 by 2, 3 by 3 is helpful. But what we can observe is that, well, if you sum together the components and then we just flip the entry to the opposite side of the diagonal, then it's still the sum of the two entries. And it doesn't matter whether we flip it first. Yeah, I'm kind of not following one straight linear explanation. So what I'm saying is that the transpose of this is aij plus, sorry, ji plus bji. But this is nothing else but the sum of the aji plus bji. And this is just aij transposed plus bij transposed. Likewise, if we have a real number c, then multiplying the matrix with c just means that every single entry in the matrix will be multiplied by c. So when we transpose this, then we see that this is just aij. Each aij has the same c that it's being multiplied by. So when we transpose this, this will just be c times aji. But this is still, every entry still has the same c. So this is c times aji. And this is c times aij transposed. So we've been able to get the c out of the out of the argument of the function. The only difference is now, I mean, as I said before, anything could be a transformation. And in this case, instead of writing t of a, this is what you would maybe expect from a transformation applied to a vector. We write a to the t. So this is just different notation, but it both means that we have an element a, and we change it to the image under this transformation. Right. Any questions? Should I draw a picture with like big matrices, or can I save the trouble? Okay, because Yuan asked in the chat about the counterexample. I think it is certainly not a linear transformation. What was I thinking when I wrote these slides? Yeah, let me. I forgot what I was thinking there. Oh yes, thank you, Jancy. That's a brilliant idea. So if you think about it, if you have, yes. So let me just do a counterexample to 4. So for a goes to RREF of a, and this is not linear. And here's the counterexample. Well, if we just the matrix 1, 1, then this is already RREF, right? So this means if we row reduce this is still 1, 1, 1, 0, 1. But if we multiply this with 2, so say 2 times 1, 0, 0, 1. Yeah, let me write this in a better way. So RREF of 2 times 1, 0, 0, 1 is equal to the reduced row echelon form of 2, 2, 0, 0. But if you reduce this is still the identity matrix. And this is the row reduced row echelon form of 1, 0, 0. So there's no 2. This is 1 times this. So this is definitely not. So this is 2. Yeah, I think you see what I mean. Okay, any other questions? Adrian, you have your hand still up. Is that a question or?
Yeah, just a quick one. So in case we'd have a question like this on the assignment, I just noticed that for your proofs, you always write it separately as like one part looking at the sums and one part looking at the multiplications. And I was just wondering if we could do the same shortcut as we did before, where we just consider like the sum of like 2 objects in whichever vector space it is multiplied.
Yeah, absolutely. You can do that.
Oh, okay.
And the reason is just, well, if the thing that you want to show holds, so if t of alpha v plus w is equal to alpha t of v plus t of w, then I mean, what if w is 0, you get axiom 2. If alpha is 1, you get axiom 1. So that's definitely possible.
Okay, cool. Yeah.
And yeah, you save time. That's true.
Exactly. That's right. Thanks.
Okay, so if there are no other questions, then let me continue, and I want to make a few definitions. So first of all, remember that we define surjective and injective for functions, and together we called it bijective. Now I want to say that a transformation is an isomorphism when it has the properties that is bijective, But this means now it's not just a function that is bijective, but it is a transformation which is bijective. So functions we don't really want to deal with functions when we talk about vector spaces, because they don't really play nicely together with the operations. That's the reason why we single out transformations, because they behave nicely with the operations. So we just upgrade the word bijective to isomorphism in the setting of vector spaces. And when there are two vector spaces which do have an isomorphism between them, then we call them isomorphic. And we're going to see later what this really means. I mean, I guess we'll just make a quick comment. So why is what does it mean? So suppose V and W is an isomorphism. Then what does that mean effectively? Andrew just asked him if iso means equal. Or you mean like the Greek word, or like in terms of math? No, here I mean linear transformation. I just sometimes forget to write linear, but if I say transformation, it means it should be linear. Otherwise, I would just say a function. Okay, so an isomorphism means that there's a one-to-one correspondence. Between elements of a V and elements of W. So basically, there's only one element associated to each element in V, and vice versa. So and moreover, so V is related to T of V, which is in W. And if we have W in W, then there's a unique say U in V, such that T of U is equal to W. So basically what this graphic should be telling you is that you can go back and forth however you like. There's not really a difference between the elements of U and of V, because there's a one-to-one correspondence. And moreover, this correspondence is compatible with the operations. So this means, say you have V1 and V2 in V, then and you sum them together, V1 plus V2. You might as well map them to T of V1, T of V2 in V, and then you can sum them together. So the plus operation, this is T. And then this means that T of V1 plus T of V2. So this means the whole story I'm trying to tell here is that if you have two isomorphic vector spaces, they're technically replaceable, because whatever you do on V, you can do on W, and whatever you do on W can be done on V. And we're going to explore this idea more, but I just wanted to give you an idea of this isomorphism. And I think you'll see in the coming slides more about this. Okay, so just the word, when the domain and the codomain are the same, then we just call this an endomorphism. But this is just really a word. And then when we fix two vector spaces, same as the space of all functions between two sets, now we can talk about all transformations between two vector spaces. So this is all kinds of transformations. So if T goes from V to W, and say F does the same, and there's another one, and then T and F are all elements in here. And so far, notice I've just said that this is a set. So anyone can define a set, and there's not really anything wrong with it. There's really very few things you could like seriously mess up when you define a set. So there's no problem with defining this. But now the exercise, which I'm probably not gonna make you do right now, but you can look at this later. The set of all transformations between two fixed vector spaces is a vector space itself. And as a hint, I mean, this is very similar to how we define a vector space structure on the space of a set of functions. So I should maybe move this somewhere else. I'm not going to shrink it too much. Let me just cut this out and create a new page for this. So now about this exercise, I don't want to do this right now, but can someone maybe tell me what the operations? So it's just as a starting point. What are operations? Or the not operations, but what are the two operations? On L, V, W. This is a calligraphic L. Any ideas?
Is it addition and scalar multiplication?
Yes. What is addition? How do we define this?
So if we have two transformations.
Yes, exactly.
Then the addition of those two transformations will be in L of V and W.
But what is it? That's the question.
What is what?
The sum. How do we define T plus F?
Is it the sum of the two matrices that define the transformation?
I have not said anything about matrices of the transformation so far.
Oh. So
I mean, you're right.
Really
you're right.
Linear, right? Is that why?
So what? The
transformations in L don't have to be necessarily linear?
No, they are.
They are?
I'm saying that they are linear transformations.
Oh, okay.
But it's the same idea as for functions. We just do this. So what I'm proposing is that that if when we apply this to a vector v, then this is just T of v plus T of w. And now this is the sum. This is the summation in W, because W is a vector space. So we have as addition of elements, and these are elements in W. Okay, and likewise we can just say that C times the transformation applied to V is equal to C times T of V, where this is now scalar multiplication in W. Okay, time is always running, and I have no idea where it goes, but so someone has suggested composition of the matrices, and we're going to get there later. But notice that this doesn't really make sense unless V is equal to W, because you can't really, if you apply T first, you'll get an element in W, and then you can apply F because F only accepts inputs from V. I was hoping to get at least through these slides. Oh, why are there so many? Okay, let's just do one by one. So now, I want to build on something that I've taught you last week, which is that we've proven that there's a uniqueness theorem, meaning that for a basis, the linear combination that we can find for any vector in the vector space, first of all, exists, and second of all, is unique. So this is what I'm saying here. There's unique representation. So I'm changing it a little bit. So please bear with me, because I realized that the meditation was kind of not really useful for the future. So now, instead of B, I'm using alpha. Just as a heads up. I hope this isn't confusing. But this is also I think the notation that the book is using. So I should have been using this all along. Okay, so what I'm now proposing is, since for any v, for any element v, any vector, we get a linear combination. I'm proposing that we assign, there are these coefficients, v1, v2, and vn, and we just assign to every vector this tuple of coefficients. And then these coefficients, we can just write them as always, an n tuple as a vector, as a column. So these are just the coefficients needed to write v in the basis alpha. And we call this the coordinates of v in the basis alpha. So this is probably the most important words in this definition. So I'm saying that there is a way to express every vector in a basis as a combination. I'm also saying, as from work that we've done before, that this representation, this linear is unique because this is a basis. So we have linear independence, and that gives us uniqueness. And then I'm saying, well, let's just call these the coordinates in this basis. And this is kind of reasonable, I guess. It makes sense because the basis gives us something to relate our vectors to. So say you want to change notation about a vector with a friend of yours, and you both have a basis, then all you need to send them is these coefficient numbers. And then your friend with the same basis elements, b1 to bn, can just build this combination with the coefficients and recover the vector. Any questions about this definition? Okay, so now that we have defined this, and we call this column, we also call this the coordinate vector of v in the basis alpha. So now that we've discussed this, that we've defined this, I'll give you 3 minutes to talk about, to think about this discussion. So I'm giving you a specific basis alpha of the polynomials p2 of r. And I want you to find the coordinate vectors. This is the notation that I'm using. Square brackets with a subscript alpha to remember which basis this is. To find the coordinate expressions of 1x, x squared, and 1 plus x. And then also for an arbitrary polynomial, try to find the coordinates expression of that. Okay. Before time runs up, let's discuss what you found. So, what is the coordinate vector of 1 in this basis alpha?
1, 0, 0.
1, 0, 0. Yes, correct. What about x?
-1, 1, 0.
Yes, correct. What is the next one? X squared. How do I find this?
0, -1, 1.
0, -1, 1. And the last one, 1 plus x. Yes, 0, 1, 0. Someone wrote in the chat. Okay. Is there any confusion about whether how we got there? Because if there's no confusion, I would actually like to move on because of time. So if you're wondering how to rewrite how we found these coefficients, then you just see like how to write these in terms of these. And we've done something similar before. So we've looked at an example discussion before we actually did this computation. So I just hope that you remember what we did there. Now, and okay, so now let's look at the maybe let's go in the bottom part of this page. Let's look at the coordinate expression of a plus bx plus cx squared in alpha. So let me maybe give you the answer first before we discuss why this is the answer. And I've already suggested here how to approach this. So once we know the solutions or the coordinate vectors to each monomial, we just multiply. We just sum them together and we multiply them with a, b, and c. So this means that we have a times 1, 0, 0 plus b times -1, 1, 0 plus c times 0, -1, 1. Now this is technically we would have to rewrite this in terms of these basis cells. So we'd have to find some coefficients. Let me use C1 times 1 plus C2 times 1 plus x plus C3 times 1 plus x squared. And then this would imply that let me move this over a little bit. So I want to find C1 to C1, C2, C3 such that a plus bx plus cx squared is equal to this, which would mean we represent it as a linear combination in the basis elements. And then the coordinate expression of this polynomial, and it doesn't really matter that these are the coefficients here are unknown. It's just a polynomial as everything else. Would be the 3 tuple of C1, C2, C3. And so now you can verify that, I mean, when we sum these together, this is going to be a minus b minus c and c. And you can verify that, in fact, this linear combination is equal to this polynomial for these values of C1, C2, C3. So I'll leave it to you as an exercise to check that these two tuples actually agree. Okay, so because time is up, let me just give you. No, let me start with this tomorrow fresh. I think there's no point in just rushing through definition. Any questions about anything that we've done so far? So maybe one last comment. So a three tuple, will always be an element in Rn. So how do I make this comment stand out? So a three tuple, an n tuple, are just vectors in Rn. And this is all I'm going to say. Okay, you're free to go, and you're welcome to ask questions. That's really too small. I don't know what part you're copying or which part you want us to look at. Adrian, you still have your hand? Oh no, he's gone. Aditya, you have a question?
Yeah. So let's say we had a basis for any vector space V. Then in that case, can we be certain that like the dimension of any other basis for that vector space would be the same as that basis that we have?
Yes, absolutely.
Mm-hmm.
Because what we've showed, what we've proven, when was it? Right. So there was a corollary in the last week, and it said that any two bases, beta and beta prime of a vector space, have the same number of elements.
Yeah. Okay. Thank you.
And in fact, that was a basis. Without this, we couldn't define the dimension as the number of basis elements because there are many bases, but the thing that they have in common is the number of elements. I see there's a question in the chat. How could we get the coefficients? Do you mean that in this calculation explicitly here that we want to get C1, C2, and C3? I don't even know if that student is still in the chat in the session. No, the student is gone. Okay. I mean, we would just solve. So we do this as we always do it. We rearrange the right-hand side so that we sort them by powers of x. And then we would get, so in front of x, you would have C2 plus C3. Actually, let me just write this down. Maybe that student will read the notes and then understand. So we have C1 plus C2 plus C3 because they're all coefficients of 1. Here, there's a 1, there's a 1, and there's a 1. And then there's various x's. So there's an x here and an x here. So we'll have plus C2 plus C3 times x. And then we only have C3 x cubed, x squared. And now if you compare left and right hand side, so you just compare them, then we get from this comparison, we get that A has to be C1 plus C2 plus C3 has to be A. C2 plus C3 has to be B, and C3 has to be C. And this is just a plain old system of equations that we can solve. And in fact, yeah, you can see that this is the solution. There's exactly one solution, which is going to be this one. Okay, I guess I could talk forever here, but I shouldn't continue when the lecture isn't happening because there's not everyone here paying attention. Like not everyone's here. Okay, if there's no more questions, then I'll just see you guys tomorrow, and then we'll continue here. Goodbye, everyone.